Okay, let's look another example. Consider the following closed loop transfer function given by this one. If a equal to 5, find the closed loop poles at k 0, 3, 10, 20, 40, and 100. And finally, the trace for 0 to, there's a mistake here. Just ignore this p because the value here is k. If the value here is kp, then this also become kp. Okay. So let us see how to tackle this question. Try to find the key point here. The key point here is the closed loop transfer function. Okay, so meaning that if we want to solve a root locus, first thing we have to do is to find the closed loop transfer function. Okay, please remember that. So why we need to find the closed loop transfer function? Because the bottom of the closed loop transfer function, which is what we call here as a den, we just give a name. The top what we call as a num. Okay, so we know that from the den, if we equate the den to 0, just like this one, this will give you this characteristic equation. Okay, so this is very crucial. So in this problem, you are given the closed loop transfer function, so you don't need to worry. If, for example, you are given the open loop, if you are given the open loop transfer function, then you must find the closed loop transfer function, because without knowing the closed loop transfer function, you cannot find the characteristic equation. So this is very crucial. Okay. All right. The next thing we have to do is say that find the closed loop poles. Okay. Another key point here is the closed loop poles. In order to find a closed loop pole stand for this, you must refer it to the closed loop transfer function. Okay. Fortunately, you are given the closed loop transfer function, which is this one, which is the CS over RS. So you need to find the roots of the den. Then you get the poles. So in this regard, the open loop transfer function, the closed loop poles is 0 here because there is no 0 here. Okay. So by substituting the value of K0, K3, K10, K21, and K40, and K100, you can solve it. For example, if K equals to 0, so S square plus 2, A is given as 5, so 5 times by S plus 4. So K is 0, so this is 0. So must set to 0. So you get S square plus 10S plus 4 equal to 0. And then find the root of this one. So how to find the root? You can use a MATLAB under this. You define the num. The num is equal to what? 5. The den equal to what? The den will be equal to 1, 10, 4. And then, so finding the command called roots for the num and the den, you get the answer. So the answer will be this one. For K0, this is the value. For K to 3, this is the value. For K to 10, this is the value. For K to 21, so and until 100. So interestingly, you see that for a low value of K, before this value, for example, you find the root is real. This is a real, this is a real, this is a real. But after 21, you see, at 21, you have a double root. This is called double root. This is called a double root. This is the double root. Okay. So you know that this is real. When a real, this is showing a overdamped case. So here I will show you a overdamped case, meaning that remember the overdamped is when the response is no oscillation, just like that. Please refer to your chapters 4 on these methods. But critical damp, this is called the critical damp. The critical damp. Okay, as you remember, the critical damp is just like overdamp, except that it is faster. And we notice that as K is increased more than 21, then the closed loop pole start to become complex. And we know that when it's become complex, then this is a case of underdamped. And if you remember underdamped, how does it look like? It look like there's an oscillation. Okay, so you see that this is the value, and as you increase the K, it is like this. And then you can plot. So you see that at K0, the root locus from here, and then the root locus will move, and then it will split out from here. So this is representation. So if you put a K for 0 to infinity, this is the locus of the roots for the closed loop poles. So this is, now you have plot your first root locus. Okay, now we look into the fifth point, locus on the real axis. Okay, meaning that if you have a pole, open loop poles, remember this poles, all these poles here is a open loop. Please remember also, root locus start, okay, root locus start from open loop poles and end at open loop 0. Okay, please remember this. Root locus start from open loop poles and end open loop 0, meaning that the pole that we are showing here is all an open loop. The root locus is the closed loop, so don't get confused. Okay, don't get confused. Okay, so let's say that this is an open loop poles, this is an open loop poles, this open loop poles, this open loop poles, and there's two open loop 0. So as we know from here, open loop, root locus start from open loop poles and end open loop 0. So how to find the locus on the real axis here? So to do that, we use an angle condition. For example, let's say we choose a point here. If we choose a point here, if this is your test point, let's say that this is your test point, this is your test point S, for example. This is your test point S, for example. The angle from here to here is 180 degrees. So meaning that, as you know that the angle condition, remember what is the angle condition for root locus? The angle condition for root locus is that it must satisfy a value of r pi, where r is plus and minus 1, plus and minus 3, plus and minus 5, and so on. Okay? So meaning that if r is 1, that means pi. Pi is equal to 180 degrees lah. Okay, please remember that. Pi is in radian and this is degrees. So this fulfill. And if you go on to here, let's say you find a test point here, for example. Let's say the point, this is test point S1. Let's say this is a test point S2. If a test point S2 here, you see that, you see the angle from this pole to here is 180. The angle from this pole to here also is 180. So the total is 360. 360 doesn't fulfill the angle condition. So that's why here there is no root locus here. Okay, think of this point S3. In the point S3 here, for example, if you choose a S point here, S3, for example, this is called S3. So you see that there's an angle of 180 from here, 180 from here, and also 180 from the 0. So it will fulfill the angle condition. And you continue to here. Here, you see that it will not, because it's 180, 180 plus 180 doesn't fulfill this one. So you see that in general, we can see that if you take a test point, you look on the right, if there is odd values of pole and 0, then it is a root locus. For example, here, if you look on the right, the poles is 1. 1 is odd numbers lah. But if you take S2, if you look on the right, how many poles? There's 2. 2 is even, so it's not a root locus. And if you take a point S3, you look on the right, how many poles and 0? 2 posts and 1 0. So the total is 3. So this is odd number. So you see, in general, we can say that odd numbers looking at the right, I write here, odd numbers of poles and 0 on the right, okay, will give me the root locus. Okay, so you can say it here. Okay, this is the condition of angle that I mentioned to you just now. Okay, the next one we want to study is about the breakaway point. The breakaway point of locus from the real axis. Okay, it is the point where the root locus originating from the opposite poles meet the real axis and break away. For example, consider the example before this. Consider the example that we were discussing before this, which is this one, okay? Okay, we look at the same example. For example, the closed loop function is this one. So if we plot, remember, we see that as the gain increase, the poles also change, and at A21, you have a double root, and after that, you have a complex root. You have a complex root, then you see that the locus basically break away. So this can be shown from here also. Okay, if you plot a graph of value of K and the value of your location of the post, you can have this graph. So the value at the real post will be is that when K equals to 0, the value of post will be at here and here. And K equals to 3 will be here and here. Just the same as what we see from here. Okay, from here. From this table. So you can plot this one and you see that